Okay, so let's start. So I was asked to quickly repeat what is circuit. And so a circuit is directed as cyclic graph, and we draw them from bottom to top. And so there is, we will use same thing as Boolean formulas and or and negation gates. And so the nodes of the graph, there are two types of nodes. There is input node and output node. So input nodes, they are labeled by an index. So circuit is a device that transforms the strings to strings. So it gets strings of a given length n in, and a circuit for functions of length n. It has an input nodes. So there are nodes that have no incoming edges. And then there is an AND gate, or there can be an ON gate. So let us do a little example of XOR. So XOR is computed by this circuit. So we need to negate this one. So this I use for negation. Like this, and this goes to an OR gate. So this is computes parity. If both inputs are equal, then output is 0, otherwise it's 1. So we can use such parts to create a circuit that computes addition of two numbers and binary. We discussed it last time. So so the least significant bit. So let's write it. If we have x and y n, then the least significant bit of so the input is x and binary, y and binary, right? And so the last bit xn is the least significant bit. And so the output will be a number with n plus 1 bits, and the least significant bits is the parity of xn and yn. And then we can continue to follow primary school algorithm. And so at each step, so to compute the next bit, we also compute the carry bit. And in this way, we can build two circuits, one that computes the output, which is here, and one that computes the carry bit. So carry bit will be 1, it will be just the AND gate. And then we continue building the circuit like this. So a circuit is characterized by two numbers. So recall what was the goal of circuit complexity. It's a simple model to for parallel computation. So we are interested in two parameters, the size of the circuit. So how big is a circuit if we want to have special circuits inside CPU, for example, for addition of multiplication. We wanted to have small size, but also small depth for fast computation. So depth is the longest path from an output to an input node. Okay. So, and we did a little exercise last time. So we thought about this primary school implementation with circuits. It will provide a huge circuit when we add n-bit numbers. So we said that the depth of the circuit was linear in n, like 6n or 10n, something like this. So if this is clear, so we can then combine the circuits to get multiplication. Right, multiplication is just iterated addition. And so we shift the number also by primary school algorithm, but this time in binary. And so one can ask again, what is the depth of the circuit when we use a naive implementation? So what will we have? Yeah, you think quadratic, and what think other?
Yeah.
Linear also. So that's better. So how do you manage to get linear?
Yeah, very easy. And just like that was looking for everything.
Yeah. So we build a circuit, but we have to do n additions. So if we use primary school algorithm, each addition will add n to sorry, I understand what you're.
No, like what you say is, I remember for every addition is like constant depth.
Yeah, but we need to make n additions after each other.
It's like n depth more than one of addition.
Yeah, so one addition
Is
depth
Each
n.
addition has depth of n, where n is a number of bits,
Yeah,
and we need to do n addition, so it's n additions of n bits number.
yeah,
And each addition is linear.
yeah. So we will, for addition, so we will output. So this is the sum one, and here we have sum n. And so you also think linear,
No.
quadratic. Yeah. So if I add two numbers, I have depth n. But then I have again to add a binary number. So I have to add n numbers for multiplication, or order n of numbers.
Oh, it's actually two n. Well, it's actually the constant.
Yeah, of course. Yeah. No, sorry.
It doesn't
Yeah.
matter, it's up to the constant, but
Yeah.
it's still quadratic, but it's.
Yeah, it's still quadratic, but you still think it's linear. No, okay, yeah. And because we have one circuit, and then we have to repeat for the third number, and each time it increases by n. But we can do a little bit better. We can do n.
Addition can be done, each addition can be done with logarithmic depth, and doing n additions can be done with logarithmic depth, just like.
Yeah. But if we want to do iterated addition, we can use divide and conquer.
Yeah.
So split over two groups that we add separately, and then we will have depth n log n. But then, yeah.
Actually, an addition can be done log n.
Yeah, indeed. That's for the seminar. So yeah, we will consider two types of circuit with bounded fun-in and unbounded fun-in. So this is our plan.
Can it be done better than log squared?
Yes. So it's the task. Well, with unbounded fun-in, you need unbounded fun-in.
And when and how we use carry bit?
No carry bits, other algorithm.
We don't use unbounded.
Yeah, I think it's open question. I need to. Actually, I forgot a little bit. So I only remember the answer. So let me think. So we need an AC1. Yeah, it will be AC1. So okay, let me define what is the class NCI and ACI. So this is important definition. So we say that so a function f, but let's define it for language so the margin doesn't work. So let's go. Also not. Yeah, it's a bit annoying because that marker it's not visible at home. So, but there is a shortage of black markers. So we say that language L. No, let's not use L today. Language A is in. So NCI circuits of are problems solved by circuits of logarithmic log n to the power I depth and polynomial size. So language A is an ACI, and this is with unbounded fan-in. Right? If there exist circuits. So note that a language is a set of strings of any length, but circuits have fixed length. So we will use different circuits for each length. So there must exist an infinite sequence of circuits, C1, C2, and so on, such that, and so here are the conditions, Cn of x is equal to indicator of whether x is in language A. So, and this should be for all x of length n.
Do you consider like, do we, when we say circuit, we mean with unbounded or bound?
Unbounded fan-in. So an ACI, unbounded fan-in.
Do we mean it by default when we say circuit? Just to clarify, like we will use circuit and so just,
Poly-size circuit, I will write it, so.
I mean, you will always talk about unbounded case.
By default, unbounded
By
case,
default unbounded case.
yeah. So there exists polynomial P, so for all n, size of n circuits, Cn is P of n. And then the third is depth. So for all n, depth of Cn is bounded by order log to the power I of n. So that's it. So let us check first property. It's written there on the board. So here is our first lemma. So can you read it at home? Is it readable, or I should copy it? So from here it looks readable. Okay, so NCI is subset of ACI. I didn't say it. Okay, I say it again. It is an NCI if there exists such a circuit, but with fan-in at most 2. So for example, the unary language, so 0 star, viewed as binary language, it's recognized, or let's use 1 star. This is when we use AC, it's an AC0, because it's recognized by just a circuit of 1 gate, the AND over all the inputs.
What does letter A mean?
Letter?
Letter A in the AC.
Yeah.
It's A.
Okay, I don't know. Yeah, so the N I know, it is NCI. So let me write, it's from Nick Peppinger, which was a guy who worked on computational complexity a long time ago. But the A, I just think they needed another letter, and they took the first letter from alphabet. So it doesn't, so they didn't want to use the U because there are uniform circuits, I guess. So it would be annoying, and also like unary language,
Use and
yeah. So there exists a lot with U.
Okay. The first inclusion is
all
clear.
circuits, all gates, and at most. Okay. So first inclusion is clear. Now let's think why second inclusion is true. So what's the problem that in AC0?
Well, because each if we have a circuit which computes a function of 10 variables, then no, we can.
Yeah, somebody is asking. Okay.
Okay,
Yeah.
if we know that each that each gate has well, it has bounded funny,
Yeah.
but since we don't have too many variables, it shouldn't be it should actually have bounded funny,
Yeah.
like probably order one.
Okay, so what we have to do is we have a gate that has an AND gate with a huge number of inputs. We know that if circuit is an NCI, the size is polynomial. So even if this gate has every other gate as input, number of gates is polynomial. And now we make the transformation. We just do a divide and conquer. We take n and pair. And so what we get is a binary tree with n gates. And the depth of the binary tree is log n.
Again, but we don't know that, like, we know that gates
So,
on the first
C
layer.
times log n, some constant c.
No, I mean, like, we know that each gate on the first layer of the circuit has fanning at most 10, but like maybe there is a layer with n inputs, then layer with like n squared.
Yeah. So we know that there exists a polynomial that bounds the number of gates. So the fan-in of this node is at most polynomial in n. So when we do take the logarithm,
C is bounded by.
yeah, so
that.
number of gates is n to the power c. Now we need to apply divide and conquer, but the list, the size of the list is at most n to the power c here.
C is not, it's not an absolute constant. It's
Yes,
bounded
it's the
by-
constant we get from this polynomial.
Oh, because.
Yeah, so it is absolute
Because
constant.
size of-
So we apply and that increases that by c log n.
Yeah.
Okay, and that means that ACI circuit can increase the depth by logarithmic factor, so it becomes NCI plus 1 circuit. And so it's open question for all the i's at least one, whether here we have strict inequality. So it might be that they're all equal. They might be all different.
So there is no. Hierarchy.
There is no high, it's open question, except for NC0, AC0. And so there is open question whether NC1, well, uniform NC1, I will explain it soon, is equal to P. So this means that there exists a log space machine that prints the circuit. And the question is, so there is extra condition, a fourth condition. And so on input n, there is this machine that uses space order log of n that prints the circuit. And the open question is uniform NC1 equal to P?
It's probably somehow connected to logarithm complexity.
Also, yeah, that's indeed. So I did preparing course on Kolmogorov complexity. It's a bit difficult to prepare nice lectures. But it will get better. Okay, and so I could add a lecture about this problem. So, but let's not speak about this. So it's easy to prove that if there exists a small circuit that can be printed with log. So if it's log space machine, that must run in polynomial time. And it's easy to see that this is a subset of P. But the question is whether it's equal to P. And so these are very simple functions. They are amazingly parallelizable. And C1, if you have such a circuit, it means a very small, like if you need it on CPU, it's very good. But whether it's equal to P, open question. There is also open question whether X is in NC1. So there's very little known in computational complexity. Okay, yeah. So this is extreme. This is such a little class. Whether it contains X is unknown. If we take, of course, uniform NC1, we know it's different because it's uniform NC1 is in P. Okay. Yes, let's try not to be distracted from program. So this is done. So let's do a few more examples. So here it's defined for languages, but we can also speak about circuits that map strings to strings. Strings of given size to strings of other size. And so I claim that HC1 contains Boolean matrix multiplication. So what is Boolean matrix multiplication? So let's say what is vector.
Addition and
Oh yeah,
multiplication.
but let's just decline. So A is in is a matrix K times M, or next K is L. So A is in this, and B is in a matrix of size L times M. And then the ijth element is equal to the OR of so it's equal to AI1, and so it's DNF formula 1J or AI2 and BJ, at least the logical thing. And here we have AIN, no, AIK. So it's L, sorry, AIL and BLG. So this is Boolean matrix multiplication. And so it is in AC1, just by definition. And so here it's written as Boolean formula, but Boolean formula is a circuit.
Why don't you don't constant depth?
Constant depth. Well, when we implement the circuit, what do we take? We first compute all the ends.
All the ends, it's one layer.
One layer, yeah,
And
but
then it computes all the ORs.
Yeah,
It's
so
another
this-
layer because we can.
AC0.
Yeah.
Because we use on the second layer, the output neuron has unbounded fan-in.
Yeah. It's N and C.
And it has two layers. So two layers is constant. So log to the power 0 is 1. Okay, so this is AC0. And now next question, what is a reachability problem? So directed reachability, so given a directed graph and two nodes, is there a path from first node to the other, to the second node? Okay, and now this question, why is it an AC1?
So the problem is given a circuit, we should.
Yeah, so you should need to come up with circuits of unbounded fan-in and depth log n that solve reachability problem. So let me write down the reachability problem. Okay, I will abbreviate it. So input directed graph. And then two nodes. U and V. And the question exists path from U to V. Okay, so how will we do this? We will look to adjacency matrix. So there is a one, and so that's a matrix. Adjacent, let me call it E, because it basically represents the edges. EUV is equal to 1 if there is an edge from U to V, and 0 otherwise. So know that here it can be asymmetric matrix. So, and then I claim that there is a directed path if identity matrix plus EUV to the power n. And so if node UV is equal to 1. So that's our so that's our main insight from which we get the circuit. So what does it mean? So UV is a matrix. It's n by n if we have n nodes. So n here is number of nodes. And so it's clear?
Yes.
Yeah. Oh, that's good.
Not plus, but, okay, if you mean plus, like, taking or. I mean, the addition means, that we take, or, by, element wise or.
Yeah. So here we have, yeah. So what we basically do is we add self loops to all the nodes. And then we check whether there is a path of length exactly n. That's the idea. Cool. If I check if everyone understands this. So this formula is correct. So the claim is there is a path from U to V if and only if element UV of this matrix is equal to 1.
And what is I? Can you repeat?
I is identity matrix. So what we do with matrix E, we change the diagonal, we put all ones there.
Mhm.
In the graph, it corresponds to self loop. And then we ask whether there is a path of length precisely n. And so it might be that two nodes are adjacent and there might be no path if n is even, for example. Then there will be no path of even length. But that's why we add the self loop, because we can go any number of times on the self loop. Okay. And so to check whether there is a path of length 2, exactly 2, we can, for example, loop to e squared. That will tell us whether there is a path of length exactly 2. Why? And so if we fill in, okay, it was not so clear, so let me explain it. And so what happens if we check matrix? Oh, and I shouldn't write matrix. What is Python notation for matrix? I forgot.
It's at.
Okay, let's use Python since many people know it. Good. No, it's not good. Let's write nothing then. Yeah, okay. Okay, so what is this? E times E. It will be the question. So here we have, and so when we look to UV, so here we will have U1 and E1V. So this will be 1 if there is an edge from U to node 1 and from 1 to node V. Okay, and then the next term will be the same, but for node 2. 2V. And so we go over all nodes. So E squared will have UV entry equal to 1 if there is a path of length exactly 2. Okay, so this is clear. So now the same for e to the power 3. It's the same logic. We check whether there is a path of length exactly 2, and then and we check all next steps by it. So it's equal to e squared times e and so on. Okay, some people are getting tired. Oh, there is a comment. Yeah, so for the notes, no, so I'm sorry, I'm in serious time trouble, so I cannot write notes, but there are notes from Artyom Parfanov from the previous lectures. So there was a question in the chat to have notes for all lectures. Yeah. So in the last lectures, I have notes already. So, and also my time trouble will be less. Okay. Yeah, but for first lecture, I insisted on notes for people with weak mathematical background, so that at least they can have the start right. Okay, so let's continue. Yeah, so now need to understand that evaluation of this circuit can be done in AC1. So our circuit needs to be of depth logarithmic. But there is a problem. We have doing one matrix multiplication costs us constant depth, and matrix multiplication costs us depth n. That's too much. We need log n. So how is solved?
Divide it.
No, this doesn't work this time. Divide and conquer. Because you need to multiply the matrices.
Well, I mean fast multiplication. We calculate I plus e power n divided by 2, and then we compute it square.
Yeah, iterative squaring. That's the idea.
Oh, I meant that. Well, it's
So we have a matrix M, and we need the nth power from it. So what will we do? We will compute m square, m to the power 4, m to the power 8. Oh, somebody wants to copy. And so on. I don't know about it. Okay, so we compute all this up to m to the power log n, but of course surrounded. And then we create the number n from its binary representation, and then multiply all the things. And so to go to the next step, we pay off one debt each time. So the total debt is logarithmic to get all these matrices. And then we have iterative multiplication of these matrices. And then we can use divide and conquer. But anyway, there are only log n times this thing. Okay, so we have proven that this is done. Oh, I forgot to explain this and this one. That's not good. Okay, but at least there are nice examples. Okay, let's do it later. Okay, let's speak a little bit more about characterization of NC0. So this is very weak circuit. We can have only bounded Fanon2, and the depth is bounded by a constant. So this is precisely functions that depend on finitely many bits. So when we have binary values 0 and 1, then this function can only depend on finitely many inputs. So is it clear? So imagine we have a language in LC1. Oh, well, let's go the 3. So we have an output node, and then we have a circuit, all nodes Fanon2, and the depth is at most a constant independent of n. So number of maximal number of input nodes that we can reach is a constant. So in the lecture notes, there is a careful definition of what it means for a function to depend on finitely many inputs. And then so it's yeah, you can read it, but the intuitive definition is clear. So I will skip it to save a bit of time. So next, I claim that the reverse is also true.
Oh, so NC0 is just like a bounded set of functions.
NC0.
For each constant, it's a finite.
Yeah. So no. And the class NC0 contains infinitely many.
Yeah, but
actually, uncountably many languages. Yeah, because we cannot compute them. So when we make the circuit bigger, we can have the different options, and so
for each
like every unary language is in NC0.
for every
No, not every okay, but you get it,
every
right?
constant C.
We can.
For every constant C, we proved that such a circuit has a finitely many number of inputs.
Yeah. So what do we know for NC0? We know that the depth here is 0 is of 1, a constant that does not depend on n for all n.
Yes. So it means that NC0 computes for NC0 with the fixed constant C computes finitely many functions.
So for each Yeah, if we fix
But
n, they
I mean,
always have finitely
many
many
functions, if we can say that if we have a function of n variables and we have functions of k variables where k is less than n, we can just throw away several, we just can throw away unused inputs. So it means that NC0 with fixed constant computes infinitely many functions, right?
For each n.
For
We have finitely,
not
but
for each
anyway.
for each
So
C.
you don't believe that NC0, the class, contains infinitely many languages?
It's in it's but not uncountable. It's countable. It should be countable because for each C, there is for each C, if we fix the constant C, there is infinitely many functions.
No, for each n, we can choose two options. For example, depending on the first bit, so we can have that all string starting with one is in the language or
it's
all
countable.
zero.
It's not.
It's uncountable
But,
because
okay,
we
but-
make countably many decisions.
Many. Okay, but then
Yeah, but anyway, this is advanced, so we shouldn't. So let's speak about it after the lecture.
Okay.
Yeah, because we cannot waste too
Okay,
much
yeah.
time. And now I forgot what I should say. The opposite direction. If there is a constant, so that for all n decisions, whether it's in the language, depend on finitely many inputs, then the class is an NC0. So if function depends on a bounded number of inputs, then we can build a circuit. And this is because what we said at the end of the previous lecture. Every function can be computed by constant, by exponential size circuit. But if we take the exponent of a constant, we still have a constant. So let me repeat, because this is also our first goal. Every function computed by a circuit of size O of n. And so what is this formula? So let us take a big N of, so we will take, so any function can be written as Boolean formula. So f of x, so here we have function that puts like there and bit inputs. And we will say that this is, we take a big N and we iterate over all A or over all Y of length N, such that f of Y is equal to 0. And then we will check whether X is equal to such Y in the formula. And if this is, we will create 0. And we can do it using a clause like in CNF formula. So the clause will check, so the clause will be, let me check, so it will be the first bit or y2 or, and here we will take, so let us say that or to the power 0 is equal to identity and or to the power 1 is just or.
Should be not the power of y of x or x.
Yes, indeed. y1 x2 to the power y2 times 1 or y to the power n of x. Okay, and let us verify that this works. So when we give, when we have an input for which f evaluates to 0, what will happen in this formula? So there will be, let us say, this equal to y. So what is yj of yj? So if yi is equal to 0, then we have identity and we have 0. If y equals to 1, then we have 1, but we negate it. So this is always equal to 0. So whenever y is equal to x, we will have an OR of all zeros. And hence this n will be equal to 0. However, if f of x is equal to 1, then each term will have at least one 1, and each term will be equal to 1. So we have a CNF that produces 1, because all the n's are equal to 1. And so this is formula of size n 2 to the power n. So size of this formula or circuit is order n times 2 to the power n. And so it's basically n plus 1 times 2 to the power n. So it's very good.
And
Okay.
it has constant density.
Yes. So it's an AC
No,
zero.
it's not an AC because it's not, doesn't have polynomial size.
Yes, sorry, good point. Yeah, yeah. So, but and it's even a homework question. So I said that if we have sparse language, then, well, I forgot what was the homework question. It's something with sparse language, and it's one of these circuit classes. Okay. So, yes. So now we have proven this one. And let's remember characterization of NC0. So I claim that if function depends on finitely many inputs, then we can implement it using NC0 circuit. And there is something nice. So here the inputs will be the set of finitely many inputs. And then we will take y for n being a constant c. So the size is exponential in c, but c is a constant, so the size of circuit is constant. And depth is, of course, also constant. Depth is even, well, and c depth is log c, order log c. Okay, so this is clear. And now we have another very nice observation. So let us consider the class of languages decided by Boolean formula of polynomial size. And this is precisely the class NC1. Okay, so how do we prove this? Okay. So first one is easy. If we have a circuit in NC1, we can convert it to Boolean formula. So what is, why is it not trivially true? What is we still have to do some work for this. So what's the obstacle? Obstacle is that in circuit, a gate can go to many other gates. But the Boolean formula is a circuit in which each part of the formula. So if you have Boolean formula, okay, let me write one. So this one is a bit small. And let's write the Boolean formula. So example, x or x1 or x2 and x3 or not x4. So this also typical for negation that we already used. And then we can have something else or not x5. So this is a Boolean formula. And then we can look to lowest priority operation and write it as a top gate. And then we go, there are two children, x5 and another gate, another operation. So next priority. So this will be OR of input x5. And here we will have an AND of two things, and there will be two ORs, and so on. So given a Boolean formula, we can directly write down the circuit.
Oh, okay.
Yeah, but there is a little problem. We need NC1 circuit, and it can be that the circuit is very unbalanced. It might be if we have a formula of size n, that the depth of this tree is n in one side. We will deal with this later. We will first speak about the other direction. So first, if we have a circuit, can we transform it to Boolean formula? And so what's the obstacle? If every gate has fan out 1, we are done, right? So we can just do the reverse transformation. But if fan out is large, what will we do? We will copy the node and recompute every gate. So if we have a circuit of logarithmic depth, then what is maximal amount of copying that can be done? And so let us first, okay, let me write it. So we are proving NC1 is in here, I mean Boolean formulas of polysize. Of polysize. Okay.
Okay, each gate is copied most polynomial many times because we copied for each output and there are polynomial many outputs for each gate. But
Okay, so let us look now to the circuit. I forgot myself, so I'm sorry, but we will find it. It should not be a problem. So here we have some inputs: x1, x2, x3, x4. And so that's something like this. Okay, we need to reuse some gates like this. Okay, let us look to a gate at smallest depth. So we need to copy it and okay, so this is depth 0. Then let's go to the smallest depth. So a note at depth D. Ah, okay, it's clear, yeah. Note at depth D. How many times can it be copied? So it is, so the node at smallest depth, how many times do we need to copy it? Well, it can be used at most 2 to the power d times this node. So at depth d, we copy
it's n
2 to the power d time, and d is equal to order log n. So after we do this copying, we have another NC1 circuit.
So each variable will be at most 2 to the d
Yeah.
where d is depth.
Yeah. So 2 to the power order log n
And then why we have
is poly n.
twin power d copies?
Most.
Because so here we have a node at depth d. And so how many outgoing wires do we have? We have at most 2 to the power d gates on top of this node on the next layer. Well, okay, 2 to the d
Wait,
minus
wait,
1 or
wait,
something, because we
But we don't know anything about bounding fade out. We only bound fade in.
so the rule is if a gate has fan out bigger than 1, then we copy this node
Yes.
equally many times as the fan out. And
Yes.
so we are bounding the fan out now, and each time we change the circuit.
We want to create a new circuit with fan out bounded by 1.
Yeah,
But like how do we then bound the number of copies? Because we don't know anything. We don't know bound for fan out in initial circuit. We only know bound for fade in, fan in.
It's an upper bound for all nodes. But
But then it's polynomial bound. No,
no, I don't understand. We need a circuit
okay,
of
how do
size.
how do we get to the power g bound?
Okay, so here is a node at that D.
Yes.
All the outgoing wires go to nodes at higher layer.
Yeah.
But we note that so we go up at most D levels. But every node has fan in too. Yes. So that means on the next, okay, on the top level, we have 1 node. On the next layer, we have at most 2 nodes. On the next layer, 4.
Okay.
Sorry, yeah, it's clear. And then 8.
Yeah.
So there are at most 2 d plus 1 minus 1 nodes No, sorry, 2 to the power d minus 1 nodes above the deep layer.
No, +1 because.
Yeah.
Okay.
Okay, so this is our first step. So when we make the copies on the next layer, we multiply, we go from n to the power size n to the power c. We move to n to the power d plus c. And now we have to do this for all the depths. So each time we add n to the power d.
So actually,
this is
only need
actually
to
a
bound
problem.
all variables for inputs. Because like if we bound number of inputs, we bound the length of. So each input is copied most 2 to the power.
Yeah, but inputs are of course not copied. We don't care about fan out of inputs.
Yes. But I mean, in formula, when we substitute it into formula, each.
Yeah, so this is still a formula. So
Each input, like, okay, just let's copy inputs too. Just to like, uniform the process. I mean, let's just convert this circuit into a tree. So each we will have 2 to the power of d, where d is the depth leaves.
yeah, so we multiply by n to the power d this size. So, but now there is a problem because we need to do this for all the layers.
Well, no, we only actually need to, well, for all the layers, but we only need to bound it for the last layer, for the first layer. Because if we bound number of copies of the first layer of inputs, how many times we copied each input, then we bound like of the entire copy.
Okay, what are we proving again? So we are in NC1. So the problem is that no, it is sorry, it is this is not the depth, but so here we have some constant. Let's call it the C prime. Okay, and now we have to repeat this for all the layers. Okay, and this is what I forgot how it works.
Each input.
Yeah, let me think. Only say if you know for sure. So yeah, of course. Sorry, yeah, it's geometric sequence. The factor that so, yeah, you're right. So we only have to look at the first layer to get the number of copies, and we know that this at most poly n. But then for the next layer, our bound will be half of so the factor that we need to multiply with is half of this. So we multiply by C prime, where C prime is the coefficients of log n. But on the next layer, we will only multiply by number of copies. We need a square root of this thing. No,
Actually, I mentioned now.
yeah.
Each input, like how many, we just compute how many times how many paths from an input to an output. It's so if there are like m ways to wave from an input to an output, then the input will be in formula at most m times. Clearly. Because for each such path, and there are at most at most 2 to the power d paths.
Yeah, cool. Yeah, of course. Yeah, sorry, I should have listened to you. So, okay. So this is nice argument to say it. Okay, so you understood what he said. So what is problem? We have a graph, a directed acyclic graph, we need a tree. And so the plan is to create, to look at each path and place it on a tree. So we look to every possible path. But so now there is directed graph, so some paths share some of the edges. But we need to count, and so to do this plan, to have a nice binary tree, we just need to bound the number of paths and then organize the path as a binary tree. And so number of paths, so when we go down from top node to bottom each time, so when we go opposite to the edges, each time number of paths doubles. So number of paths will be polynomial. And then we reorganize these paths by repeating nodes and then in a nice binary tree, and this is size polynomial. So that's how we see that this doubling process that we execute, it will not blow up the size.
No, why is polynomial if we double?
It's double, but we have logarithmic paths, so it's
okay.
2 to the logarithmic.
Yeah. Okay, so thank you. This saves the lecture, well, at least this part of the proof. We have proven, well, one direction is now proven. Now we need to prove, oh my God, it's then, okay. So now we need to prove other direction. So we want to say that a Boolean formula is a subset of MC1. So Boolean is in NC1, and here poly side. So we have Boolean formula, and we already discussed what is the problem when we translate it to a circuit. It can be unbalanced circuit of linear depth, like we had when we did addition. So what is our plan? So imagine we have a very unbalanced circuit. Let me draw one here. So, so here is an input gate, and then we have something like this, and so on. And one more level here. Okay, what we will do is think about circuits as model for parallel computation. So when we have such a computation, the plan is to split the computation using a node G and run the computation starting from G in parallel with the computation below G.
Then take the results.
So we don't know what is the output of this node, but to start a computation, we try both values, like you say. So we will run 3 computations, but in parallel. That's the plan. So G equals 0, G equals 1, and what is below. And then when we know what is the real G, we pick the correct evaluation of this circuit. So what we use is we consider 2 circuits. So we consider C1, C0, C1, and C for G. Here a circuit that evaluates node G. And then our answer will be C0 and or let's say it's C1 and CG, or C0 and not CG. Yeah, so if C0 says CG output 0, then this will be equal to 1. And the output will be, and this will be 0, so this doesn't count. And so the answer will be C0. And if GZ equals outputs 1, it will be the answer of C1. Okay.
This idea is actually used in the actual CPUs.
I didn't know, yeah. Okay, and so what is
why we inverse CG in the
yeah.
Yes.
So when the output So if output of C, so if this part evaluates to 0, then we want the result from this evaluation with this gate set to 0. Okay, so if output of CG is 0, then the answer must be this thing. So if it's 0, the negation will be 1,
Okay.
and then the end is like this. Okay, so now let us understand how we can, what are the details of our depth reduction strategy. So first we have to choose what is node G. And so let us say what is the size of the node. Size of node is number of nodes below this node. And I claim that there is a node of size, and so if whole circuit has size S, we can find a node of size in the interval 1/3 S, 2/3 S. So here is interval of integer numbers, at least S over 2, 2/3 S. So we can find the node that whose size is at least 1/3 of S, at most 2/3 of S. So S is everything, the size of the whole circuit. Why is it? So start in the root node. Size of this node is S. Okay, let's in the size include the node itself. So size is S, and we go down each time on the heaviest child. So then the size will decrease. And then I claim that let's look to the highest node that still has size at least 2S over 3. One of his children must have size at most S over, let's look to,
No, it's right. We look at the highest. We look at node with size that
at least,
at most to
yeah. So the lowest node, the lowest node with size at most 2S over 3. And one of his children will have,
size at least S.
yeah, so the first node that has size at most 2S over 3, and then the heaviest child has size at least S over 3. And that will be our G. So that's how we break the circuit. So each time, so what is the number of times we have to break our circuit? Okay, I say that if we keep breaking our circuit, we end up with a circuit of size.
Because each time when we break the circuit, we decrease its depth.
Well, when we break this, so
We don't know that.
so well, we know it's polynomial, the depth, and so each time we go from depth S to depth 2/3 of S. So in the beginning, the depth is at most
Wait.
S.
Why? S is size, not depth.
Yeah, but in the beginning we bounded that by the size.
Okay.
And each time when we do depth reduction, we go to depth S 2/3 of S plus 2. Because here we have to do a few extra things. We don't count the negation gates. And so then one can calculate, okay, there's careful calculations in the node. I made a nice inductive hypothesis. And then you see that the logarithmic number of such reductions will again you up with logarithmic depth. It's a bit annoying because there is this +2 there. But okay, as long as S is bigger than 3, you can bound it by 3/4 or something. As long as S is a big number. If S is small, we don't care what's happening because of big O notation everywhere. And so, okay, this is okay. So, yeah, so if it's not clear, just there is nice inductive hypothesis and other argument in the lecture note. So it is just a calculation of the depth. Okay. So now, yeah. So let us, I will, so there are 15 minutes left. So I will not, I will skip this, so then I can maybe merge two lectures in one, because we started 3 weeks late, it's kind of sad to cover so few materials. I will just briefly explain what this means. So what is L is problem solvable in log space. So here we use special machine. It has input and output tape. Input tape, the machine cannot write on the input tape. So the input is always of linear size. So to get logarithmic space, we need to do something with the input. So just useless tape, and we say that read write head is always above input string, or maybe one cell further. And for the output, well, output is yes or no. So okay. So we don't need to deal with, there is no output tape. Okay, this is class L. Class NL is the same, but for non-deterministic machine. So here is L and NL. So there are two transition tables, transition function. So what is uniform NC1? It is the same as this definition of NC1 with FAN2, but there is a machine that prints out the circuit, and this machine can use logarithmic space. But now this machine also has output, because the circuit is a big thing, it's more than 1 bit. And for the output, you have to be very careful. So there is a common mistake in some papers. So output is written on output special output tape, and the head can move in only one direction. So once the output is written, you can no longer see it. And this is important distinction. Okay. So if we have such log space transducer, sometimes called, so such a log space machine should print the circuit, and then these circuits should satisfy these conditions. So then it is in uniform NC1, and this class is in L. And so the main idea we have to do there is so we have log space reduction. So what is a log space reduction? It is just the machine I just described with logarithmic output, and it maps certain input to the certain output with a special output tape. And then the combination of two log space reductions is again a log space reduction. And here it's important that a machine cannot return on the output tape to get this thing. And so how it happens is that it's quite difficult, because when you perform first reduction, then the second machine, so in a log space reduction, you can read the input many times, but the output can only be written once. So when we compose two such reductions, we have to be careful. The second reduction cannot ask what was the output of the first reduction again, because output so we have only a log space machine, and in logarithmic space you cannot store the output. So what happens when we simulate? So we simulate the second machine, and the idea is that each time he needs to see some intermediate calculation from first reduction. We fire the first reduction on separate tape, or in parallel track of the tape, until we get it. And so a combination of reductions, a log space reduction is also log space reduction. And this is the idea of first inclusion. So we first print the circuit, which we view as a reduction, and then we run the decider. And we do the same thing whenever it needs to know. So then we have an algorithm that evaluates the circuit. But here we have NC1 circuit. So well, actually we can transform NC1 circuit to Boolean formula. And then Boolean formula has logarithmic depth, and we can store the branch. Or we can use composition of reductions, the same idea. Okay, I won't ask about this, I'm just explaining. L in NL is clear. And then NL is in uniform AC1. So what is the idea here? So AC1, uniform AC1, definition is clear. So given a problem in NL, how can we build a circuit? And here we need to understand that NL can be viewed as reachability graph. So here we have non-deterministic log space Turing machine. So we need to think how many configurations there are. And then look to the graph, directed graph consisting of all configurations. And we connect two configurations if machine goes from one step to the other step in this configuration. So, but why do we have polynomial configuration, polynomial amount of configuration? This is by definition of log space machine. So if it has logarithmic memory that it can use, then number of states is constant to the power log, which is polynomial. So all and also position of the read-write head on the input tape is polynomial. So if machine is in NL, then it has polynomial size configuration graph, and then we run our AC1 circuit for reachability. And the good thing is that this circuit is kind of really simple, but okay, then you need to carefully check the details. But to build the circuit, actually, you only need one bit from the input. And so it's a very easy reduction. And then again, so you build circuit, then evaluate circuit. It's a composition of two circuits that are each in AC1. Well, first to build the configuration graph, it's NC0 circuit, and then composed by AC1 circuit to check reachability. Reachability is we take start state configuration of Turing machine, and then we check whether it reaches some accepting configuration. Okay, this
If
is
we want to make a circuit, we need to know all the tree in NL. And tree in NL takes n. No.
So we need-
Two in power n.
Yeah,
nodes.
but for tree, it's about this inclusion. Here there is no tree, there is directed graph that is configuration graph. And we need to check whether start configuration goes to accepting configuration.
We talked about configuration, not about nodes.
Well, each configuration is a node.
Mhm.
And then one configuration is connected to another one if machine goes in one step to this other configuration. And then we have to check whether we can reach accepting final configuration. So this is the idea, but I shouldn't be talking about, okay, I think I will fail to do everything. So to prove all this, but okay, let's say what is P/poly.
You defined it on the other lecture.
Yeah, on the other lecture, but I will define it again because I think most people forgot about it. So I define it and then I will tell only this proof. And then it will be 5 minutes too late for the lecture. Okay, and the definition is basically on the board because we just drop this for the depth. And so we have no restrictions on the depth. And we so this P/poly. So that was fast. And now we have to understand that P is in P/poly. So this is important theorem. P in sorry, subset of P/poly. So here we have a set of languages here too, and if a machine can solve it in polynomially many steps, we can build a polynomial size circuit. And so know that circuit is what in your CPU on your computer, but the problem is circuit goes into loops on your computer. So how can we get rid of the loops? Then just think about putting all CPUs above each other. And when there is a loop, you go to the next CPU. So this is crazy way, of course, to compute something. Like you run your laptop for one step and throw it away and then go to the next one. But in principle, it's a circuit. So if you compute for polynomial many times, you need polynomially many laptops, and you end up with a cyclic circuit of polynomial size. And so that's what the proof is saying. But let's do it like formally, a bit more formal. So, so we have configuration of Turing machine. Yeah, so that's we have computation head. And so so the head is about one cell. And so let's encode it as a sequence, but let's encode the head together with the cell where it's located. And so we will encode every cell as a pair. So imagine that this has A, B, A, C, D, D, and so on. So we will encode it as A and the default symbol if if head is not there. But then here the head is located and it's in state Q, we encode it as this. And so here we describe machine just by a list of cells. We know machine runs in polynomial time, so it's enough to use, so assume machine runs in P of n time. So we will just use P of n cells. Well, one more because we want to know what happens after the last cell, and our head is so it always goes right. We need to encode Q, so we need one more cell. Okay, so so now we can code our machine as a string of length. So configuration is string of length P over n over some finite alphabet. And now, when we consider the mapping, one configuration to next configuration, it's a mapping from strings of this alphabet to strings. But note that our next configuration, so we will have A prime dash. For example, if machine goes right, what will we have? The same thing here. But now machine will be in. So if we have B dash here, and then we will have B Q prime. And so machine reads A, writes A prime, and goes to the right. So this is what happens. Yeah, so you need to, if you don't see. Okay. So what we see is that in this string to write down the next cell, we only, so each cell depends on at most 3 cells from the previous layer. So this is kind of similar like NC0 function. And so we map strings over general alphabet to strings of general alphabet of fixed length. Then we only modify and each new cell depends only on finitely many cells. Well, it's not really an NC0 because our discussion is actually only for binary languages. But this is not an obstacle, because here we have finite alphabet. We can code it as binary string, just any mapping, and we use constant length to encode each cell. So this can be viewed as binary string, and still each bit on the output depends on only finitely many bits here. And we know because of our first result that we can implement it with NC0 circuit. Okay, so what we do now is we have our input. So we prepare a string that encodes the input. And so in the tape, there is 0, 1, 0, 1, whatever, the input string. And we encode it according to our sequence in binary. Also can be done by NC0 circuit, because each cell depends only on one input bit. And then we run the computation, and then we check with the big AC0 and, with AC0 circuit, whether there is accept state. Somewhere appeared as final state in the computation. There's also constant depth, AC0 circuit. And so when we combine all this, we have a circuit, and I claim that the circuit is of size order Pn squared. Right? Because each string is of length Pn, order Pn, and we need to simulate for Pn steps by definition that our language is in P. So we start with the language decided in polynomial time P of n. Okay, and that's how we built the circuit. That's the full story. Okay. So it's precisely the, and so we have proven this thing. Yeah, and P isn't P slash poly.
Demonstrators, I think.
Yeah. Okay, but I can say why circuit set is NP complete, and the next lecture I will say do the reduction to 3 set. And then next time we can start. This is very good. We can do most about just a little. Okay, so now let's consider circuit sub problem. Just 5 minutes. So what is this problem? So I think you can guess it, right?
Okay, we're given a circuit.
Yeah. So
We
circuit.
decide if it's satisfied.
Yeah, set the input circuit phi, and then question exists x for which phi of x equals to 1. Okay,
In the logic, the input, can you repeat, please?
yeah. So we are given a circuit phi. It receives n bits as input, some number n bits as input, and we check, can we find bits that make circuit evaluate to 1?
Okay.
Okay. So what will be the reduction? So we start with the problem A that is in NP. And so we know that there exists certifier definition. So V, XC, and so we have a verifier. So exists V verifier. It's polynomial time machine, and we know X in A, if and only if there exists a C that makes verifier XC accept. And it's polynomial time verifier, which means that it runs in polynomial time in the length of the first argument, X. And so polytime in X. Okay, now we will build a circuit. We make a circuit that simulates V in the same way as we proved P slash poly. And so this circuit has 2 arguments, X and C. So what is reduction? So now given X, so we want to reduce A to circuit set. So we need reduction. A needs to be mapped to circuit set. So that means we get the string X, or let's say a string W, and let's change the variable because we use that. So we get the string W, and we need to make a circuit phi W. Phi W is satisfiable if and only if W is an A. So what we do, we have our circuit from P slash poly that simulates V. It has 2 inputs, this circuit. And so here we have constructed the circuit, but it's a special circuit, let's call it psi, because it takes W and C as input. We only have 1 verifier, 1 circuit, but here for every W, we need a different circuit. What will we do? We will hardcode W in the first argument. So this will be equal to psi of W, and here is just so let me write it better. So we will have phi of W C will be equal to psi of WC. I'm just saying we hard code the first argument. So we get a circuit that receives any certificate. And if the certificate is accepted, it evaluates to 1. And that's our reduction. That's it. It's finished. And so let us verify that And so what we have here is there exists C such that VW accepts, and by construction, it means that there exists C such that circuits phi WC accepts. Just by construction, phi simulates our circuit psi, which simulates V, but with first argument hard-coded. And that's the proof. Okay, so you want me to repeat something? Ask now.
And then we convert the circuit into a formula.
Yeah, so now we have proven that Y and A, if and only if, phi W is satisfiable. So this is what we achieved. And the proof goes in these steps here, by these two. C is certificate. So, yeah, if W is in the language, then here there is a certificate.
What is the definition?
Yeah, fine. So it's accept two binary strings. W is our problem input, is W and A. C is verifier certificate from definition of NP.
And what means
It's a string, it's a string
hard code to the V?
W. So we have a circuit, it has a long list of inputs. And there are two parts of the inputs. W inputs corresponding to first argument and the inputs corresponding to C. And then we will hard code. That means that we create constants according to the bits of W and we feed them into the gates of psi. So we reduce the number of inputs by generating constants. So to generate constant, we just take whatever gate x1 and then connect it to the end. So to get 0, we make end of x1 and not x1. Okay. So x1, and here we have not x1. So that's how we create constant 0. Okay, that's technical detail. And the same with OR for getting a constant 1. So we create the constants and we feed them according to the bits of W. So when we build reduction on input W, just compute the circuit psi, which is a fixed procedure that we just got from this proof that P is in P/poly. So we only don't know that circuit exists, but it's easy to compute for every input length. So we run this computation and then we fix a part of the input.
And this will not work for another V.
Yeah, so our circuit W, the output of reduction only works for this W, but the psi works for all W.
Why?
It is the reduction we got when we proved that P is in P/poly. So here we have a language, but only with one argument, but we can always split the argument. So that's our plan. We split the input and then we do the same construction. And so we view the verifier as a language in P that gets pairs, and then we get the circuit. Yeah. Okay, you need to think a little bit about it. It's okay. It's a lot of information. So note that these two lectures merge, but there are careful lecture notes. So it's normal that next lecture will also difficult. But then you have, yeah, please go ahead.
Yeah. The next step is to reduce this problem to percent.
Yeah. So we have proven this one, but not yet this one. I will explain next lecture in the beginning.
No, we proved that this problem is NP complete.
Yeah. Circuit set is NP complete. Okay, clearly it's an NP because we have witnessed the certificate. So verifier just evaluates the circuit on the assignment. And so it is NP complete. Okay, so we went 10 minutes over time, but we almost recovered one lecture, which is very impressive. So I think it's because of good seminarists. You can go a bit faster. And next lecture, I will start with the small reduction from circuit size to 3-sat. So from circuits to formula, it's not so difficult. And then we start with proving that certain games are p-space complete. But first, let's have 10 minutes break. So let's remind. For 7:50, it's seminar.
Let's see this NP part.
So we take any problem A and NP. So NP hard means that every problem in NP reduces to this problem. So we started from any problem in NP. And we use that it has verifier.
And then so can you repeat why we can do it for all V?
Yeah, for all W.
Yes, yes.
So verifier gets pair of strings and then say yes or no. So verifier decides on the language of pairs. So we prove that P is in /P poly. So we can get the answer from verifier using a circuit. So circuit has pairs as input and output accept or reject according to what verifier is doing. And so the circuit psi works for all pairs W and C. So this we can always believe for all the W. And so now we are good because we have this equivalent.
And now for what we.
And so because fixing W is the same, and so this is the same as psi WC. And so it's equal to, well, it doesn't accept it, it's equal to 1. Of that.
Yeah, I think I got it.
Yeah, that's important because it's a very important theorem. But circuits, it's the first NP complete problem. So now there is one small missing link, and then all the tree is validated from previous lecture. Okay.
Thank you.
Very good. Yeah, very